G'day, space enthusiasts! I am Dr. Sachi Vale, and you are tuned into Science Aura. Today we are embarking on a profound journey to the very edges of our solar system, following the historic trails of Voyager 1 and 2. Launched nearly half a century ago, these twin spacecraft have surpassed all initial expectations, venturing further than any human-made object in our history. Originally designed for an ambitious grand tour of the outer planets, capturing those breathtaking first close-up images of Jupiter, Saturn, Uranus, and Neptune, their mission evolved. They became our first interstellar scouts, piercing the invisible veil of our cosmic neighborhood to explore the uncharted, freezing territories of the Milky Way, far beyond the sun's comforting warmth. To truly understand the magnitude of their current location, we must first define the boundaries of our solar neighborhood. Our sun is not just a source of light and heat. It is a dynamic, active star that constantly exhales a stream of charged particles known as the solar wind. This continuous outward flow creates a massive magnetic bubble that envelops all the planets in our system. This colossal bubble is called the heliosphere. Think of it as a protective shield, a cosmic windsock inflated by the sun, pushing back against the interstellar medium. The interstellar medium is the matter that exists in the space between the star systems in a galaxy. It is composed of gas, dust, and cosmic rays. For decades, scientists wondered where exactly our solar bubble ends. The boundary where the solar wind is finally stopped by the pressure of the interstellar gas is known as the heliopause. Before reaching this absolute boundary, the solar wind undergoes a dramatic transformation. It travels at supersonic speeds for billions of kilometers until it crashes into the interstellar medium, creating a turbulent, chaotic region called the termination shock. Voyager 1 crossed the termination shock in 2004, and Voyager 2 followed suit in 2007. As they passed this milestone, the solar wind abruptly slowed down, heated up, and became significantly denser. This marked their entry into the heliosheath, the outer layer of the heliosphere where the solar wind is compressed and becomes highly turbulent. Navigating through the heliosheath was a journey into the unknown. The spacecraft instruments detected complex magnetic structures resembling a sea of massive magnetic bubbles. This turbulent zone acts as a primary filter for galactic cosmic rays, which are high-energy particles originating from distant supernovae. The heliosheath deflects a vast majority of these dangerous particles. As the Voyagers continued their relentless outward trek, scientists eagerly awaited the signs of the true boundary, the heliopause. But what would this boundary actually look like? Theoretical models suggested a gradual blending of solar and interstellar materials, a smooth transition zone where the sun's influence slowly fades away into the cold, dense environment of the wider galaxy. However, the data sent back by the Voyagers would soon rewrite our textbooks. On August 25th, 2012, Voyager 1 detected a sudden dramatic change in its environment. The steady stream of solar particles it had been measuring for 35 years plummeted to near zero. Simultaneously, the intensity of galactic cosmic rays spiked to unprecedented levels. This was the moment of historic significance. Voyager 1 had officially crossed the heliopause, becoming the first human-made object to enter interstellar space. It was a monumental achievement for science and humanity. The transition was not the gradual fade that some had predicted. It was a sharp, distinct boundary, a definitive edge to the protective bubble of our home star. Despite crossing into interstellar space, Voyager 1 was still within the gravitational grip of the sun, far from the Oort cloud, but it was bathing in an entirely new cosmic environment. The instruments recorded a surrounding plasma that was significantly colder and denser than the plasma inside the heliosphere. This confirmed that the interstellar medium was pressing hard against us. 6 years later, on November 5th, 2018, Voyager 2 made its own historic crossing. While Voyager 1 had exited the northern hemisphere of the heliosphere, Voyager 2 exited from the southern hemisphere. This dual crossing provided scientists with a stereoscopic view of the heliopause, revealing that the boundary is asymmetrical and constantly shifting in shape. Unlike its twin, Voyager 2 still had a working plasma science experiment when it crossed the boundary. This instrument allowed scientists to directly measure the temperature, density, and speed of the interstellar plasma for the very first time. The data revealed a complex interplay between the solar wind and the interstellar medium, characterized by intricate magnetic interactions. One of the most surprising discoveries was the alignment of the magnetic fields. Scientists had expected the magnetic field of the interstellar medium to be oriented differently from the magnetic field inside the heliosphere. However, both Voyagers found that the interstellar magnetic field was largely aligned with the solar magnetic field, a phenomenon that still puzzles researchers today. This unexpected alignment suggests that the heliosphere is not just a simple bubble, but a structure that deeply influences the surrounding interstellar space. The sun's magnetic reach extends far beyond the heliopause, subtly organizing the chaotic interstellar medium into a more ordered state. It is a testament to the immense power and influence of our relatively small yellow star. Before crossing the heliopause, Voyager 1 encountered a bizarre region dubbed the Magnetic Highway. Here, the map Shanlutifuse sees from the sun connected directly with the magnetic field lines of interstellar space. This connection allowed high-energy solar particles to escape into the galaxy, while simultaneously allowing galactic cosmic rays to flood into the outer heliosphere. The magnetic highway was a completely unexpected phenomenon, forcing astrophysicists to rapidly revise their models of the outer solar system. It demonstrated that the heliopause is not a solid, impenetrable wall, but a porous, dynamic boundary capable of complex particle exchange. The Voyagers were fundamentally changing our understanding of space physics with every data packet sent. Beyond the magnetic anomalies, the raw interstellar environment presented new challenges and revelations. The cosmic rays measured outside the heliosphere are incredibly intense. These subatomic particles, traveling at nearly the speed of light, are the shrapnel of exploded stars. They carry immense energy and pose a significant radiation hazard to any future interstellar mission. By measuring the true intensity of these galactic cosmic rays, the Voyagers highlighted just how crucial our heliosphere is for life on Earth. Without this massive magnetic shield deflecting the majority of these harmful particles, our planet would be subjected to a relentless bombardment of high-energy radiation, potentially stripping away our atmosphere and sterilizing the surface. The data from Voyager also revealed that the interstellar medium is not uniformly quiet. It is periodically disturbed by massive shock waves originating from the sun. When the sun experiences a coronal mass ejection, it sends a powerful wave of plasma hurtling outward. These waves can travel for years before crashing into the heliopause and rippling through the interstellar medium. Voyager 1 detected several of these interstellar tsunamis. When a shockwave hits the dense interstellar plasma, it causes the plasma to oscillate, generating faint radio emissions. By capturing these emissions, the spacecraft's plasma wave instrument was able to determine the density of the surrounding space, confirming that the density increases the further we move from the sun. This increasing density is a fascinating counterintuitive discovery. One might expect space to become emptier the further you travel, but outside our solar bubble, the material from the broader galaxy is compressed against the heliosphere. The Voyagers are currently sailing through a region where this compressed galactic matter is highly concentrated, offering a unique field of study. The journey of the Voyagers is a testament to human ingenuity and our insatiable curiosity. When they were launched in the late 1970s, the technology on board was state-of-the-art. Yet by today's standards, a basic smartphone possesses millions of times more computing power. Despite this, these robust machines continue to transmit invaluable scientific data across the void. The radioisotope thermoelectric generators on board are powered by the natural decay of plutonium-238. As this radioactive material decays, it generates heat, which is then converted into electricity to power the spacecraft's essential systems and scientific instruments. However, this power source is finite, and the generators lose about 4 watts of power every year. To conserve the dwindling energy supply, mission engineers at NASA have had to make difficult decisions. They have been systematically shutting down non-essential systems and even the heaters that keep the scientific instruments from freezing in the harsh cold of deep space. Remarkably, some instruments have continued to function at temperatures far below their tested operational limits. The data transmitted by the Voyagers travels at the speed of light, yet it takes over 22 hours for a signal from Voyager 1 to reach the antennas of the Deep Space Network here on Earth. This immense communication delay highlights the staggering distance these spacecraft have traveled. Every bit of data we receive is a faint whisper from the very edge of our known cosmic frontier. As we look towards the future, we must accept the inevitable reality that the power supply will eventually drop below the minimum threshold required to operate any instruments. Within the next few years, the Voyagers will likely fall silent, ceasing to transmit data back to Earth. It will be a poignant moment for science, marking the end of an era of unprecedented exploration and discovery. Even after they stop communicating, the Voyagers will continue their silent journey through the Milky Way. They are on trajectories that will take them past other stars in the distant future. In about 40,000 years, Voyager 1 will drift within 1.6 light-years of a star in the constellation Camelopardalis, while Voyager 2 will pass near the star Sirius in nearly 300,000 years. Attached to the side of each spacecraft is a golden phonograph record, a time capsule intended to communicate the story of our world to extraterrestrials. The golden record contains sounds and images selected to portray the diversity of life and culture on Earth. It includes greetings in 55 languages, the songs of humpback whales, and the timeless music of Bach and Chuck Berry. The golden record is a profound symbol of human hope and our desire to connect with the cosmos. It represents a message in a bottle cast into the cosmic ocean, a testament to our existence long after our civilization may have faded. The records are designed to last for billions of years, potentially outliving the Earth itself, preserving the memory of a small blue planet orbiting a yellow star. The loss of the Voyagers will leave a significant gap in our observational capabilities. Currently, there are no immediate plans or funded missions to send another dedicated probe into interstellar space. Any future mission would require decades of travel time just to reach the heliopause, meaning the data currently being gathered is uniquely precious and irreplaceable for generations to come. Scientists are meticulously analyzing every byte of information the Voyagers send, knowing that this stream of data will soon run dry. They are studying the subtle variations in plasma density, the shifting magnetic field lines, and the sporadic bursts of cosmic rays to build a comprehensive map of our local interstellar environment. This map will be the foundation for future astrophysics. The heliosphere itself is moving through the interstellar medium, much like a boat moving through water. This motion creates a bow wave ahead of the heliosphere, compressing the interstellar magnetic field and plasma. The Voyagers are providing the first direct measurements of this complex interaction, helping us understand how our solar system navigates through the galactic environment over millions of years. Our solar system resides in a region known as the local interstellar cloud, a wispy expanse of gas and dust spanning about 30 light years. The data from Voyager suggests that we may be approaching the edge of this cloud and transitioning into a different interstellar environment. The properties of this new region remain a mystery, one that the Voyagers might just glimpse before they power down. The transition from the local interstellar cloud into a potentially hotter, less dense region could have subtle effects on the shape and size of the heliosphere. If the external pressure drops, the heliosphere might expand. Conversely, if we enter a denser cloud, the protective bubble could be compressed, potentially allowing more cosmic rays to penetrate into the inner solar system where Earth resides. These long-term astronomical changes highlight the importance of understanding our cosmic neighbor. The Voyagers are not just exploring distant space, they are helping us understand the fundamental forces that shape the environment of our own planet over geological timescales. They have transformed astrophysics from a purely observational science into an experimental one, probing the galaxy directly. One of the most profound realizations from the Voyager missions is the sheer scale of emptiness in interstellar space. Even at their incredible speeds of over 60,000 kilometers per hour, it will take them tens of thousands of years to cover the distance to the nearest stars. This vast emptiness underscores the isolation of our solar system and the immense challenges of future interstellar travel. Despite this emptiness, the space between stars is filled with a web of magnetic fields and a thin mist of plasma. It is a dynamic, active environment governed by the laws of plasma physics. The Voyagers have revealed that magnetic reconnection, a process where magnetic field lines break and reconnect, releasing explosive energy, occurs even in the cold, sparse environment of the interstellar medium. This revelation of widespread magnetic reconnection helps explain the heating of the interstellar plasma and the acceleration of cosmic rays. It shows that the fundamental physical processes we observe near the Sun and Earth operate universally across the galaxy. The Voyagers have effectively extended our terrestrial laboratories into the vast expanse of the Milky Way, proving the universality of physics. As the power levels on the spacecraft continue to drop, the engineering teams face increasingly complex challenges. They must carefully manage the thermal environment of the spacecraft to ensure that vital components do not freeze. They have developed ingenious software patches and operational procedures to squeeze every last drop of science from these aging, magnificent machines before they succumb to the cold. In recent years, the teams have had to turn off the heaters for the cosmic ray subsystem and the low-energy charged particle instrument. Astoundingly, these instruments continue to return data even after their temperatures plummeted well below -50°C. This resilience is a stunning testament to the robust engineering and rigorous testing conducted by the original builders in the 70s. The attitude-controlled thrusters, which keep the spacecraft's antennas pointed towards Earth, have also shown signs of degradation. To compensate, engineers successfully fired up a set of backup thrusters on Voyager 1 that had not been used in 37 years. This incredible feat of remote engineering extended the mission life by several years, allowing us to gather even more invaluable interstellar data. Every maneuver, every command sent to the Voyagers requires meticulous planning. The communication delay means that an emergency cannot be addressed in real time. If a problem occurs, the spacecraft must autonomously protect itself until instructions from Earth arrive nearly 2 days later. The software running on the vintage computers is a marvel of autonomous fault protection and deep space survival. The Deep Space Network, a global array of massive radio antennas, is essential for maintaining contact. As the Voyagers move further away, their signals become increasingly faint, requiring the most sensitive receivers on Earth to detect them. The network must constantly upgrade its capabilities to catch the incredibly weak whispers from the edge of interstellar space amid the background noise of the universe. The scientific community is keenly aware that this era of direct interstellar observation is drawing to a close. There is a palpable sense of urgency to extract every possible insight from the incoming data streams. Researchers from around the world collaborate to interpret the complex signals, debating the implications of fluctuating plasma densities and magnetic anomalies that defy conventional theories. One major unresolved question is the exact shape of the heliosphere. Is it shaped like a comet with a long trailing tail, or is it more spherical, like a bubble? The data from the Voyagers, combined with observations from other missions like IBEX, suggest a complex, possibly croissant-like shape, sculpted by the flow of the interstellar magnetic field. We are mapping a structure we can never see directly. As we piece together this puzzle, the Voyagers remain our only direct touchpoints with this distant reality. They represent the ultimate triumph of human curiosity, extending our senses billions of kilometers into the dark void. They have transformed our understanding of the sun's place in the galaxy, revealing that our solar system is a dynamic entity, constantly interacting with the wider cosmic environment. The legacy of the Voyager mission goes far beyond the data and the photographs. It has inspired generations of scientists, engineers, and dreamers. It has taught us that with ingenuity and perseverance, we can reach beyond our immediate horizons to explore the unknown. The story of these twin probes is a narrative of human ambition, a testament to our relentless drive to understand the universe we inhabit. When the final instrument is powered down and the transmitters fall silent, the Voyagers will not cease to exist. They will transition from active scientific observatories into silent monuments of human achievement. They will wander the Milky Way for eons, enduring the harsh conditions of deep space, carrying the golden record as a permanent testament to the civilization that built and launched them into the dark. Imagine a distant future, millions of years from now. Our sun may have changed, our planet may be unrecognizable, but the Voyagers will still be out there. They are arguably the most permanent physical legacy of humanity. If another spacefaring civilization ever intercepts one of these probes, they will find a beautifully crafted message from a species that dared to reach out across the immense cosmic void. The data we continue to receive today is a precious commodity. Every fluctuation in plasma density, every spike in cosmic radiation is carefully logged and analyzed. These measurements are crucial for designing future interstellar probes. If we ever hope to send a spacecraft to Alpha Centauri or beyond, we must first master the environment that the Voyagers are currently traversing with such incredible resilience. The concept of an interstellar mission was once purely the realm of science fiction. The Voyagers have made it a scientific reality. They have proven that it is possible to build machines capable of operating for decades in the most extreme conditions imaginable. They have set a gold standard for reliability and autonomous operation that modern spacecraft engineers still strive to emulate in new planetary missions. The transition across the heliopause was not just a physical milestone, it was a psychological one for humanity. For the first time, we had definitively breached the protective cocoon of our star system. We stepped out into the true cosmic ocean. The measurements taken during this crossing will be studied for centuries, serving as the foundational texts for the emerging field of interstellar astrophysics. As we analyze the interstellar magnetic field, we are learning about the broader structure of our local galactic neighborhood. The orientation of these fields hints at the violent history of nearby supernovae and stellar winds that have shaped this region over millions of years. The Voyagers are acting as deep space archaeologists, uncovering the explosive history of our corner of the Milky Way galaxy. The plasma waves detected by the spacecraft provide clues about the density and temperature of this ancient interstellar gas. By studying how these waves propagate, scientists can infer the properties of the medium, much like how seismologists use earthquakes to study the Earth's interior. The Voyagers have turned the vast emptiness of space into an acoustic chamber, listening to the subtle vibrations of the cosmos. The stark reality of their power depletion is a constant reminder of the limits of our current technology. The plutonium power sources were a marvel of their time, but they decay relentlessly. Every year, the spacecraft have less energy to keep themselves warm and to power their transmitters. The engineering teams must perform a delicate balancing act, prioritizing the most critical scientific instruments. There is a poignant irony in their journey. As they travel further into the most fascinating and unexplored regions of space, their ability to observe and report back is slowly diminishing. We are sending our blind and deaf emissaries into the dark, relying on their last fading whispers to illuminate the unknown. It is a race against time to gather data before the cold, and the silence finally overtake them entirely. The legacy of these missions will endure long after the signals fade. The data they have provided has fundamentally altered our understanding of planetary science, heliospheric physics, and interstellar mechanics. Textbooks have been rewritten, entirely new fields of study have been born, and our cosmic perspective has been permanently expanded, all thanks to these two modest spacecraft launched in the 70s. Consider the sheer audacity of the Voyager mission. It was conceived in an era before modern computers, before the internet, before we had even a basic understanding of the outer solar system. Yet, through brilliant engineering and visionary planning, humanity managed to construct vehicles capable of piercing the boundary of our star system and surviving the incredibly harsh conditions of the interstellar void. The communication protocol used to talk to the Voyagers is a marvel of signal processing. The spacecraft transmitted a power level of barely 20 watts, roughly equivalent to a refrigerator light bulb. By the time that signal travels billions of kilometers to Earth, its power is a fraction of a billionth of a watt. The Deep Space Network antennas must isolate this faint signal from cosmic noise. This incredible feat of telecommunications requires supercooled receivers and massive parabolic dishes, pointing precisely at the spacecraft's coordinates. The Earth's rotation means the signal must be seamlessly handed off between tracking stations in California, Spain, and Australia to maintain a continuous connection. It is a global effort to keep the lines of communication open with our interstellar ambassadors. The loss of contact will be a somber milestone. For decades, the daily telemetry from Voyager 1 and 2 has been a constant heartbeat, a reassuring sign of our presence in the deep cosmos. When that heartbeat finally stops, we will be truly cut off from the interstellar medium until a new generation of probes can be designed, funded, built, and sent on the decades-long journey to reach the heliopause again. While there are proposed concepts for new interstellar probes, none are currently ready for launch. These future missions aim to travel faster and further, equipped with modern sensors designed specifically to study the interstellar medium. However, until they launch, the Voyagers remain our sole source of direct data, making every remaining day of their operational life incredibly valuable to the scientific world. The Voyagers have essentially become a bridge between generations. The scientists who originally designed the mission have largely retired or passed away, handing the baton to a new generation of astrophysicists who were not even born when the spacecraft launched. This continuity of knowledge and dedication highlights the collaborative and enduring nature of grand scientific endeavors that span multiple human lifetimes. The heliopause is not a static boundary. It breathes in and out with the solar cycle. During the solar maximum, when the sun is highly active, the solar wind is stronger, pushing the heliopause outward. During the solar minimum, the boundary shrinks inward. The Voyagers have observed these subtle shifts, confirming that our solar bubble is a dynamic, living structure that responds to the magnetic moods of our star. This dynamic breathing means that a spacecraft could theoretically cross the heliopause multiple times if it was situated right at the boundary during a solar cycle shift. However, the Voyagers are moving outward so rapidly that they have decisively left the boundary behind, plunging ever deeper into the undisturbed interstellar medium, where the influence of the solar cycle is completely overshadowed by galactic forces. The cosmic rays that the Voyagers are now measuring are primary cosmic rays, pristine particles that have not been altered or deflected by the sun's magnetic field. Studying these primary rays provides crucial clues about the origins of the universe, the mechanisms of supernovae, and the fundamental nature of matter. It is like sampling the raw, unfiltered atmosphere of the galaxy itself for the very first time. These high-energy particles are incredibly dangerous to biological life and complex electronics. The fact that the Voyager's vintage electronics have survived decades of exposure to this radiation is nothing short of miraculous. It speaks to the robust design choices made in the 70s, utilizing heavily shielded, hardened components that can withstand an environment far harsher than anything found in low Earth orbit. As we reflect on the journey of Voyager 1 and 2, we must also acknowledge the profound sense of perspective they have given us. They turned their cameras back towards Earth in 1990 to capture the famous pale blue dot image, showing our entire world as a single, fragile pixel suspended in a sunbeam. It is a humbling reminder of our place in the vast, indifferent expanse of the cosmic arena we inhabit. The pale blue dot image encapsulates the philosophical impact of the Voyager missions. We are a small species on a small planet, yet we possess the capability to build machines that can outlast our civilizations and carry our memory into the stars. The Voyagers are the ultimate expression of human hope, a physical manifestation of our desire to understand the universe and to leave a lasting mark upon the cosmos. The data from the interstellar medium also helps us understand the conditions necessary for life in other star systems. By studying how our heliosphere shields us from galactic radiation, we can better evaluate the habitability of exoplanets orbiting other stars. If a star lacks a strong stellar wind to create a protective astrosphere, its planets might be constantly sterilized by deadly cosmic rays from the galaxy. Therefore, the Voyager missions are not just about exploring our own solar system. They are providing critical baseline data for the burgeoning field of astrobiology. They help us define the parameters of a safe harbor in a galaxy filled with violent, high-energy phenomena. Our sun's protective bubble is a crucial ingredient in the recipe for life, and the Voyagers have shown us exactly how that massive bubble operates. The interstellar magnetic field measured by the spacecraft also plays a role in the formation of new stars. Magnetic fields can support clouds of gas and dust against gravitational collapse, regulating the rate of star formation in the galaxy. By measuring the local magnetic field strength, the Voyagers contribute to our understanding of the grand, slow-motion processes that dictate the life cycles of stars in the Milky Way. Every new piece of data is a puzzle piece fitting into the larger picture of galactic dynamics. The Voyagers are charting the currents and tides of the interstellar ocean. Just as early terrestrial explorers mapped the oceans of Earth, these probes are mapping the vast, invisible structures of space, providing navigation charts for any future generation daring enough to attempt a crude journey to neighboring star systems. The resilience of the Voyager hardware is legendary, but the software is equally impressive. The computers on board have a fraction of the memory of a modern digital watch, yet they handle complex navigation, thermal management, and data formatting. The engineers on Earth continually optimize this software, uploading incredibly efficient patches to squeeze maximum performance out of this severely limited computing architecture. These software updates are transmitted incredibly slowly, at a rate of just 16 bits per second. It takes days to upload a simple command sequence, and days more to verify that the spacecraft received and executed it correctly. It is a slow, methodical conversation across the cosmos, requiring immense patience and precision from the dedicated team of engineers who meticulously oversee the aging spacecraft's daily operations. The impending silence of the Voyagers is a stark reminder of the immense scale of the universe and the limitations of human technology. We have managed to touch the very edge of our solar system, but the vast majority of the galaxy remains completely inaccessible. The distance to the nearest star, Proxima Centauri, is over 4 light years. At its current speed, it would take Voyager over 70,000 years to reach it. This staggering timeline highlights the necessity of developing new propulsion technologies if we ever hope to become a true interstellar species. Chemical rockets and gravitational assists, the technologies that propelled the Voyagers, are simply too slow for practical interstellar travel. Concepts like solar sails, nuclear thermal propulsion, or even antimatter drives will be required to bridge the immense gaps between the stars. Until those revolutionary technologies are realized, the Voyagers will remain our furthest outpost. They have paved the way, proving that the boundary of the heliosphere can be crossed, and providing the crucial environmental data needed to design the next generation of deep space explorers. They are the pioneers, the trailblazers who ventured into the dark unknown so that others might eventually follow in their historic wake. The scientific community is preparing for the inevitable day when the signal is lost permanently. It will be a day of mourning, but also a day of immense pride. The Voyager mission has been an unmitigated triumph, exceeding every metric of success. The data archives will be preserved for future generations, serving as a permanent record of humanity's first tentative steps out of our solar cradle and into the wider cosmic ocean. Even as the instruments fail, the spacecraft themselves will remain intact. In the vacuum of deep space, there is no air resistance to slow them down, no weather to erode their metal frames. They are pristine artifacts, perfectly preserved in the freezing void. Barring an incredibly unlikely collision with a wandering asteroid or comet, they will continue their outward trajectory unaltered for millions, perhaps billions of years. The golden record attached to them is heavily shielded to protect it from micrometeorite impacts and cosmic radiation. The cover contains highly specific instructions, written in a universal scientific language of mathematics and physics, explaining how to play the record and detailing the location of our solar system relative to 14 incredibly stable pulsars. It is a cosmic treasure map leading directly back to our home world. The inclusion of the pulsar map was a subject of intense debate. Some scientists worried that broadcasting our exact location to unknown extraterrestrial intelligence could be dangerous. However, the prevailing sentiment was one of optimism. The creators of the Golden Record believed that any civilization advanced enough to find and retrieve the Voyager spacecraft would likely be peaceful and scientifically curious, much like ourselves. The music on the Golden Record ranges from classical masterpieces to indigenous folk songs. It was curated to represent the vast emotional and cultural spectrum of humanity. Imagine an alien species millions of years from now listening to the intricate melodies of Bach or the driving rhythms of Chuck Berry. It is an attempt to communicate our essence, our creativity, and our soul across the unfathomable barriers of time and space. The images encoded on the record show human anatomy, our cities, our ecosystems, and our scientific achievements. They portray a vibrant, complex world teeming with life. If Earth were to face a catastrophic event, the golden records on Voyager 1 and 2 might be the only surviving evidence that our civilization ever existed. They are humanity's backup drive, safely stored away in the ultimate off-site vault of interstellar space. As we approach the end of their operational lives, we reflect on the immense scientific return on investment. The Voyager missions were originally budgeted for a 5-year grand tour. Their incredible longevity is a triumph of engineering and a testament to the dedication of the mission control teams who have meticulously nurtured these probes through decades of unforeseen challenges, technical glitches, and the harsh realities of space. The data from the outer planets completely revolutionized our understanding of the solar system. Voyager discovered active volcanoes on Jupiter's moon, Io, the complex ring system of Saturn, the tilted magnetic fields of Uranus and Neptune, and the diverse icy moons that orbit these gas giants. They rewrote the textbooks on planetary science before they even began their secondary mission to explore the edge of the heliosphere. Their transition from planetary explorers to interstellar observatories was a seamless evolution. The instruments designed to study planetary magnetospheres proved surprisingly capable of analyzing the heliopause and the interstellar medium. It is a remarkable example of scientific adaptability using existing tools to measure phenomena that the original engineers could barely conceptualize when the spacecraft were being built on Earth. The ongoing analysis of Voyager data continues to generate new scientific papers every year. Even as the stream of new data slows, the archival data holds undiscovered secrets. Advanced computational techniques and new theoretical models allow scientists to re-examine old measurements, extracting subtle signals and patterns that were invisible to the analytical tools of the 1980s and 90s. The discoveries are far from over. The story of the Voyagers is deeply intertwined with the human desire to leave a legacy. We build monuments, write books, and compose music to ensure we are remembered. The Voyagers are the ultimate monuments, constructed not of stone, but of aluminum, titanium, and silicon, designed to endure the ultimate test of time in the unforgiving environment of deep space. They are our silent sentinels, forever watching the distant stars. As the plutonium power sources continue their irreversible decay, the internal temperature of the spacecraft will slowly drop until the propellant lines freeze. Once the thrusters can no longer fire, the spacecraft will lose their ability to keep their high-gain antennas pointed at Earth. That will be the definitive end of the mission. The signal will be lost, not because the transmitters failed, but because they can no longer aim at us. This loss of pointing accuracy will happen silently, billions of kilometers away. On Earth, the giant antennas of the Deep Space Network will continue listening, but the faint whisper will simply vanish into the background noise of the cosmos. It will be a quiet, dignified end to an incredibly noisy and productive mission. The Voyagers will slip into the dark, continuing their journey without our watchful eyes to guide them forward. The scientific community is preparing for this inevitable silence. There are no immediate plans for a replacement mission. The vast distances involved mean that even if we launched a faster, more advanced probe today, it would take decades to reach the interstellar medium. The Voyagers are a unique, irreplaceable window into the cosmos. And when that window closes, we will be temporarily blinded to the realities of interstellar space. However, the legacy of the Voyagers will inspire future generations of engineers and astrophysicists. The data they have provided will form the baseline for any future interstellar exploration. They have proven that it is possible to build robust, autonomous machines capable of surviving the harshest environments in the universe. They have set a standard of excellence that will challenge space agencies for decades, perhaps centuries to come. The Voyagers have taught us that the solar system is not a closed bubble, but a dynamic, permeable structure interacting intimately with the galaxy. They have revealed the complex magnetic highways, the dense interstellar plasma, and the relentless bombardment of cosmic rays. They have transformed our understanding of our place in the universe, showing us that we are just one small part of a vastly larger, interconnected cosmic ecosystem. As we bid farewell to these remarkable machines, we must also celebrate their immense achievements. They have carried human curiosity further than ever before. They have expanded our horizons and challenged our assumptions. They have shown us the beauty, the complexity, and the sheer scale of the cosmos. The Voyagers are not just spacecraft. They are an extension of the human spirit, reaching out into the dark unknown with unwavering resolve. The story of Voyager 1 and 2 is a testament to what we can achieve when we push the boundaries of technology and dare to dream big. It is a story of international collaboration, brilliant engineering, and an insatiable desire to understand the universe. The data they have gathered will be analyzed for generations, continuing to yield new insights into the fundamental nature of space, time, and the origins of our solar neighborhood. Even in their silence, the Voyagers will continue their mission. They will carry the golden record, a message of peace, and a snapshot of our civilization into the distant future. They will wander the Milky Way, silent ambassadors of a small blue planet that once dared to reach for the stars. Their journey is far from over. It has simply entered a new, silent phase, a permanent voyage through the endless expanse of the interstellar ocean. We may lose contact, but we will never lose the profound knowledge they have bestowed upon us. The boundary has been crossed, the textbooks have been rewritten, and our perspective has been forever altered. The legacy of the Voyager mission is eternally etched into the annals of scientific history, a glowing beacon of human achievement that will inspire every future endeavor to explore the uncharted territories of the grand cosmic arena. Thank you for joining me on this incredible journey to the edge of the heliosphere and beyond. I am Dr. Sachi Vale, and this has been Science Aura. Keep looking up, keep questioning the unknown, and remember that even in the vast, cold emptiness of space, the spark of human curiosity continues to shine brightly. Until next time, stay curious and keep exploring the wonders of our magnificent universe. Goodbye for now, space enthusiasts.